Today we are going to discuss about the compensation theorem. Okay, so this is the last theorem we are going to discuss in this chapter. So I am sharing my presentation. This is the few weeks. Okay, so compensation theorem. The name itself it is saying that in this theorem we are going to compensate the one branch with another another thing. Okay, so let us take. Okay, it just states that. Okay, any linear time invariant network when the resistance R of an uncoupled branch carrying current I means in a one resistance the current flowing to that resistance is current I is changed by delta R. If there is a change in the resistances, I mean either it may be increased, either may be decreased by delta R. The current in the all the branches will be changed and can be obtained by assuming that an ideal voltage source of DC is connected in such that VC equals to I into delta R. That means we have to replace all the circuit, that is R plus delta R, the total one, okay, can be replaced with the current flowing to the previous one, okay, into the product of delta R. Okay, so V equals to IR. So the current flowing to that one and multiplied with the change in resistance. That is, if there is some changes, that is, if we can product those two and we can place that VC, okay, in series with the R plus delta R when all the sources in the network replaced with their internal resistances. If internal resistance is not known, all the voltage sources are replaced with the short circuit, all the current sources are replaced with the open circuit. Okay, so in a simple words, why? Because that's a statement. In a simple words, we can say that if we have a branch with RL, okay, the current flowing to the branch is I, okay, I can replace this one, okay, with a voltage source. The value of that voltage source is V equals to IR, okay. So the current entering is this one. If I place plus and minus means the direction of the current is obviously opposite to the this voltage source. So I have to prove the two things, okay. So I have to replace this resistance with a voltage source. The value of that voltage source is I in R. In this situation, the sources, all the sources must be replaced with their internal resistances. So I can explain within explanation. Why? Because whether they both are same or not. So we have to prove with an example. Okay. So let us assume a load of RL which is connected to a DC network whose Thevenin equivalent gives the V0 as a Thevenin voltage and RTH as a Thevenin resistance as shown in the figure. Okay, fine guys. In the first circuit, what I shown in the before. Okay, this one, the source network I'm considering as a Thevenin equivalent circuit. In the Thevenin equivalent circuit, V0 is the voltage, RTH is the equivalent resistance. The current flowing to this one is I. Okay, so from this network, I is defined as V0 by RTH plus RL. Okay, the direction of current is in downwards. Okay, next, if I replace it, I mean, if I increase the resistance, that is RL plus delta R. Okay, so delta RL may be the increment in resistance or decrement in the resistance. Okay, so if I increase or decrease the resistance, the change in current is I dash. For the same network, I am increasing the resistance with the delta R. Okay, by the change in the resistance, there must be a change in the current. That change in current is I dash. Okay, so this can be replaced with a this network. That is what the compensation theorem says. Compensation theorem states. Okay, so this whole network can be replaced like this. Okay, so in this case we have a two resistances RTH and the RL plus delta R. So the same resistances can be placed. The current value I dash can be replaced with the delta I. The V0, the voltage source can be replaced with the VC. The equivalent value of VC is equals to I into R. Okay, that is I into delta R. Okay, next, the source, that is V0, can be replaced with the internal resistance. In this situation, we don't have any internal resistance, so that I am replacing the source with the short circuit. So in this circuit, the current I dash equals to V0 divided by RTH plus RL plus delta RL. Okay, so which I represented with the equation 2. Okay, so this is your first current I, this is your I dash. For the same one, delta I becomes as a I dash minus I. Okay, why? Because the difference in the both the circuits will use the change in current. Okay, so I am substituting the I dash and I values which are defined in my previous equations. So I substituted over here, taking the LCM. Okay, so LCM, finally RTH articles will get cancelled, RL gets cancelled. So finally we get delta RL in the numerator. In the denominator I'm separating. So V naught divided by RTH plus RL I'm separating, and delta RL, what will the remaining thing in the numerator I'm writing in delta RL by RTH plus RL plus delta RL. Okay. So as we know that, okay, so V naught divided by RTH plus RL, that is V naught divided by RTH plus RL we defined as a I. So I'm replacing this V naught divided by RTH plus RL with a I. Okay, so I'm representing this as equation 5. Okay, as I said earlier, the compensation theorem, the compensated voltage VC is equals to the current flowing through the network I into product of the change in resistance when all the sources are inactive. Okay, so the same thing we got it. So I equals to delta RL, sorry, VC. I can replace this I into delta RL with a VC. Okay, so the equation comes as a delta I equals to minus VC divided by RTH plus RL plus delta RL. Okay, the negative term says that, okay, so if the current is passing from positive to negative, which is opposing the actual direction current. Okay, I will explain. Okay, so in this connection, the current is passing from X to Y. If I replace with that with this voltage source, means the direction of the current is opposite to the previous direction, that is Y to X. Okay, so that only the negatives comes into the picture. Okay, fine guys. The compensation theorem. I'm just briefing the all the statements which we learned from the statement and the explanation are the compensation tells that the change in branch resistance, branch currents changes, and the change is equivalent to an ideal compensating voltage source in series with the branch opposite to the original current, and all the sources in the network being replaced with their internal resistances. That is what we proved. Okay, so with a simple example, I can show you our compensation theorem. Okay, the compensation theorem, in this network we have a 16-volt voltage source and a 2 ohm to 2 ohm resistances are 3 and a 4 ohm resistance. If we apply KVL, we can get the currents values. Okay, so the 4 ampere current is flowing through 2, and 2 ampere current is flowing through 4 ohm, and the 2 ampere current is flowing through these two resistances. Okay, so I can replace the last branch, which is the 2 ohm resistance, can be replaced with the voltage source. The direction of the voltage source, the positive, if the current direction is from, if I consider this as an X terminal, this as an Y terminal, means the direction is from X to Y. So I have to place X as a positive, Y as a negative. If the direction is opposite, means I have to place this one as a negative, this one as a positive. Okay, so I can replace this resistance with an equivalent voltage source, that is V equals to IR. The current flowing to this one is 2 ampere, the resistance is 2, so V equals to IR, so 2 into 2, that is 4 volts. So I can replace this with a 4-volt voltage source. Okay, so this is your compensation theorem, guys. Hope you are understood the compensation theorem. Okay, be safe guys, have a nice day, thank you.